This is Jim Hendershot again, ready to present lecture number 8 on one of my favorite topics, electric machine performance discussion of electric machine performance. We're all familiar with the basic 3 laws that describe the principles of energy conversion in motors, plus the details of material properties. But what I would like to do is to take that theory that you all pretty well understand and convert that into a simple explanation of how motors convert electrical power into mechanical power, or vice versa for generators. So there's a little better way to maybe get your hands around the concepts to help us as an introduction to motor design. And let's start by pointing out again that all electric machines must have 2 active magnetic components. One component has to be a stator, which is mounted to the earth through some mechanical parts such as frames and feet and bases and all that sort of thing. And inside that stator has to be a controllable electromagnetic field. I guess it's possible to put magnets in there as well. There are some designs that have magnets and electromagnets in the same field for control. Then the other component that is necessary is the rotor, and the rotor has to have a magnetic circuit in it as well, or at least be magnetic in the case of some machines. Now the non-salient pole machines have active magnetic components in each of the 2 components. And the flux linkage between these 2 is what converts the energy and causes torque and shaft rotation. The salient pole machine doesn't require any active magnetic created field in the rotor. The rotor only acts as part of the closing of the circuit, you might think of it that way, of the field in the stator. The permanent magnet machines use permanent magnets in the rotor to provide the magnetizing flux. Wound field synchronous machines that are similar in configuration to the permanent magnet machines, but they have poles on the rotor, soft iron poles with coils around them, and DC power is applied to those coils through an external power source through slip rings and brushes to present the magnetizing field from the rotor. Now induction machines, the magnetic field from induction rotor has to come from the magnetizing flux created from one of the current vectors in the stator. So the stator produces all the current, and some of that current is used to magnetize the circuit, and the rest of the current is induced to flow into the cage of the rotor, and the adjustment of that provides the adjustment in torque. Salient pole machines, all the magnetizing flux is created by the current from the stator. This is my favorite illustration to show the mechanics of how a motor really operates. If we look here for a moment at this picture on the left here, this blue line represents our air gap between the rotor and the stator. And the motion of these components is not quite right. They move in this direction on the motor, but it's easy to illustrate it this way. Each one of these is a magnet with a north and a south pole, and their orientation is important here. If we orient these across the air gap such that you have south poles facing south poles, they want to push apart. All of you have played enough with magnets to know the feeling and the sense of that. The same polarity pushes these apart. If you turn them end for end so that you have north poles facing each other, they are pushed apart. So that's repulsion. Now if you put one north pole facing a south pole, there's a big attraction. Okay, now let's mount all those things in a machine, a permanent magnet machine. We've got this set of magnets are converted into electromagnets in the stator. a soft iron pole piece with a coil wrapped around it. Okay, these magnets are actually glued onto the rotor core. So we see the same effect. We see the north pole of a stator attracting the south pole of the rotor, so that's putting a counterclockwise torque on this rotor. It's attracted and it wants to line up. This magnet wants to center on that electromagnet. So on this side, on this pole, we have this south pole is repelling the south pole on the rotor. And as it's repelling, it's starting to attract this north pole. So the south pole wants to align itself on this north pole, and this north pole wants to align itself on the south pole. But when it gets in that position, what we do is we start to commutate it. We turn that coil off and turn this set of coils on, and then it wants to align itself again through repulsion and attraction, and then we turn this phase off and turn the third phase on, and the process continues and rotation continues. So there's a very nice graphical way to keep a picture of this in your head forever, so you know how the motor works. And induction machines are far more complex than that, but they basically work the same. Here's a couple lousy pictures of induction machines, and here you have the poles in the stator are still electromagnetic, and the poles on the rotor, they're electromagnetic also, but they're still there in shape and position, just like in the permanent magnet machine, except they're not glued there. They're induced there. They're created in the soft iron of the pole, so you say have the exact same attraction, repulsion taking place. It's going the other direction here, but there's a slip. The slip of the induced poles on the rotor don't rotate the same speed and synchronism with the rotating stator field. Now, in the case of reluctance machines, this shows a picture of a switch reluctance, but the principle is exactly the same for reluctance synchronous as it is switch reluctance. You create electromagnetic poles in the stator. It doesn't matter whether they're north or south. The highly permeable salient poles on the rotor looks kind of like a gear in this case. Those salient poles are going to be attracted by the stator, and the stator poles in rotation occurs and is commutated the same way as permanent magnet machines are. So to summarize, the PM machines, it's important to consider the permeance coefficient, the thickness of the magnet relative to the thickness of the air gap. That's very important, because what this all boils down to is all we have to do, the principle of designing a machine then is to determine how much flux you create in any of these machines, and then to get the right flux linkage you have to determine how much current times number of turns you need to get the flux linkage to create the torque you want. So it's basically the same for all machines, and it's easiest probably to explain it with a PM machine if we look at this same C-shaped soft iron circuit that we had before, except that remember in one of the earlier lectures we did put a magnet here, but this is a better picture of it. This shows a magnet, the same cross-section as this part of the magnetic circuit. So I'll show you on the next slide how you determine the flux density of the magnet using the load line or the permeance coefficient. But that flux goes through the circuit and jumps across this air gap, hopefully, and continues to flow around there. And we want to know how many lines there are, so you take the flux density of the magnet that you've selected times the area of the magnet, which is this area of the face of the magnet as it touches the pole, and the area times the flux density gives you total lines of flux. And you can use the total lines and determine what the flux density is in other parts of the circuit, including the air gap, by dividing those total number of lines by whatever cross-sectional areas there are. Now here's how you calculate what B sub in the gap is. if in our example here, if we put a big piece of steel in here, so there's no air gap in this circuit, all the flux from this magnet is easily flows around here with no leakage, and the flux density would be that value right there. And by the way, this is a BH curve, a second quadrant demagnetization curve of a typical rare earth magnet that you would buy. And magnets have high hysteresis, so they were magnetized in this quadrant, and then when the field was turned off, this much magnetized this much flux density remained in the magnet. So that's what we have to work with. So in a closed circuit, that's our B sub R. That's the flux that we have available for our flux linkage. But we have to have an air gap. You always have to have an air gap. You either put conductors in the air gap, or you have to have a clearance between the rotor and the stator so it doesn't rub. So there's always an air gap. So how do you determine what the flux is in the gap? Well, you plot on the h-axis the air gap, and you plot on the b-axis the thickness of the magnet, and where those you project vertical and horizontal, and where they intersect each other, you draw the permeance line, the load line. You draw a line from the ordinate up through that intersection of where those two air gap and magnet length values intersected, and continue on until it intersects the BH curve, and then where that intersection takes place, project horizontally back over to the vertical axis, and that's the flux you're going to have. That's the flux density you have in the gap. That's how you determine that. Here's an example of that that I want to clarify a point about energy product. All magnets you buy, they're all rated or talked about. You know, a 38 grade magnet, that's 38 megagauss oerseds. A 50 grade, 50 megagauss oerseds. 45 megagauss oerseds. 20 megagauss oerseds. Whatever. That's a decent way to compare one magnet to the other. But old textbooks used to teach that you design the length of the magnet and the air gap to operate at the maximum energy product. This gives you the lowest cost magnet. Now that may be true, but it also gives you low flux, and so that's a bad strategy for motor design. You don't want to design motors at BH max, which would be here in this case. The maximum energy product, that means this value times that value, where that is maximum is about 45 degrees from the ordinate here. So if that were your load line, if our load line went through here, and if I projected that's where I'd have an air gap the same thickness as the magnet, and if I projected that over to here, I'd only have 0.64 Tesla flux in the gap, and that's crazy to do that. Plus, I'd have a problem with demagnetization. That's even more important. With that big of an air gap and that thin of a magnet, I'd have a problem with demagnetization at temperature. We'll go into that later, however. So you want to make the air gap as small as possible. What that does is that pushes this load line up as high as possible. Remember, plot air gap here and magnet thickness here, and project the load line. So I get at this load line, I got 0.8 Tesla in the gap. If I make the air gap smaller or the magnet thicker, I even have higher flux density in the gap. Let's take cases where, for whatever reason, you have to have a large air gap, like a case in point is a high-speed motor where you need a retainment sleeve to hold the rotor together, so you need a big air gap. So you could compensate for that somewhat by just making the magnet thicker. You don't have to accept the lower flux density just because you have to have a bigger air gap. Just make the magnet thicker. Sure, it costs money. Now, machines without magnets, like induction motors and reluctant synchronous machines, since you're not buying a magnets and you don't have a data sheet for what the flux density is, you have to assume a flux density that's based on what you desire that flux density to be. And typically in induction motors, I think most induction motor engineers would opt for as high as they can get. They probably like to have 0.8, 0.9 Tesla in the air gap. You can't always get it for manufacturing reasons. It might be as low as 0.65. I think it's safe to say that big motor companies like GE and Westinghouse and Reliance and Siemens and companies like that, they probably in their engineering department have a number that they always use to start with, to start with their designs. They always assume they're going to get 0.8 Tesla in the gap or 0.75, and so that's how they go forward to proceed with the design to determine how many turns per coil they need and what the air gaps are and what the magnetizing current has to be. And it's the same technique you'd use for a reluctance machine. In the case of reluctance machines, you need ampere turns. You can calculate the turns and current based on the ampere turn requirement for whatever the air gap permeance turns out to be. There is a certain amount of Ni or ampere turns required to drive the flux through the iron itself, and the shorter the path, the less that is. The longer the path, the bigger that is. But the ampere turns required in a reluctance machine to magnetize the iron is a fraction of the ampere turns required to attract those poles across a big air gap, those salient poles. So the ampere turns required to magnetize the iron when the circuit is closed or when the poles are aligned is usually neglected or disregarded. So this is a kind of a cross-sectional picture that, in conclusion, that shows a reluctance machine here. This shows a cross-section of the stator, 12-slot stator with the coils in place for one of the phases, and they're full pitched. Full pitched means, we'll talk about more about this later, but if I take the number of slots in the stator and divide it by the number of poles, whatever that turns out to be, that's a full pitch. So if you have 12 slots, you got 4 poles, that's 3 teeth. So if you span 3 of those teeth, you've pitched the coils at full pitch. So that puts them at the center of the 4 poles in the rotor. And where are the 4 poles in the rotor? Where the 4 poles are on this rotor where the flux is most happy to go. And that we'll call that the direct axis. So the flux generated from the stator wants to go this way and that way, see? It wants to go in the path of these flux carriers. It doesn't want to go in the quadrature axis because it's got to go through the path of these flux barriers, and it doesn't like to go that way. It likes to go that way. So the key, as we'll see later, the key to a successful design of this kind of a machine is to make the acceptability of flux in the D-axis as favorable as possible compared to the Q-axis. Let's put that another way. The inductance ratio needs to be very high. We want high inductance in the D-axis and low inductance in the Q-axis. We want the ratio of the saliency. That's how happy it is to have poles. Saliency. We want a high salience ratio. So that concludes this lecture. Thank you very much.